So let's talk about artificial gravity, more horizontal circles. Karin, one method of generating artificial gravity in outer space would be to build a circular space station and spin it. So here's a side view. You would stand on sort of the wall, but for you it would feel like that was the floor. And there's a top view. Let's analyze this. If the space station has a radius of 35 meters, what does the period of rotation need to be for an astronaut to experience 80% of Earth's gravitational field? I like this question. I like this question. I like this question. I also like this question because it's outer space and I'm a space nerd. First question. Aiden, what does this question want me to find? Period. What letter in our circular motion acceleration equations is period? Okay, it wants us to find capital T, not lowercase t time, capital T. So I already know, I don't think I'm using the v squared over r version of circular acceleration. I'm using the 4 pi squared r over, okay. For an astronaut to experience 80% of Earth's gravitational field, any thoughts on how I might want to start this out? What was that? Even before that. Karin, what? I think I'm going to do a free body diagram, but did they give me a picture? I'm going to label the picture. I'll label the right-hand top view picture, I think. So here's the person. What are the forces acting on them? Oh, wait a minute. Are we in outer space? No mg. Okay, don't fall for that. What else? Well, what path is this person tracing out? A circle. Where must there be a net unbalanced force pointing? Toward the... So Aiden, I know there's an arrow pointing that way. What force is that? Now you might say, isn't that Fc? That doesn't show up on my free body diagram. That's like saying F net showed up on your free body diagram. It does not. What force is pushing me in a circle? That's the key to doing this question. And that's my question for you. What's pushing me in a circle? Can I give you a hint? Friction? That's what we call the force from a surface? What do we call the force from a surface? What? What was that? Loud and proud, loud and proud. Ah, normal force is what's pushing me in a circle. The floor is. In fact, if I was standing on a scale, the scale would be pushing me in a circle, but what does a scale measure? Normal force. So my equation is going to start out like this. Normal force is what's pushing me in a circle. And F equals what? So I'm moving in a circle. It's going to be MAC on the right-hand side. What about the left-hand side? How big is the normal force? How would I write 80% of gravity? Well, I don't do math with percentages. I always make them decimals. So what's 80% as a decimal? How would I write 80% of gravity? 0.8 times, not times 9.8, because then you would be saying acceleration equals force, but 0.8 times mg, because that's the force of gravity. Although, wait a minute, look on the left. Is there an m on the left-hand side? Is there an m on the right-hand side? Is there an m in everything? Could little kids and grown-ups live on this space station and be okay? Well, that's handy. So on the left-hand side, I have 0.8 g. On the right-hand side, I have AC. Which version of AC am I going to use? 4 pi squared r over t squared. Aiden, what did you say they want us to find? Which letter was that one in my big equation here? Where is the t right now? On the... Bleh! Wait. I can multiply it to the top on the other side, yes? I can rewrite this as t squared equals 4 pi squared r over 0.8. I also divided the 0.8 and the g down. Yes? T what? Hey, how to get rid of a squared? By the way, as far as I'm concerned, if you look at this equation right here, I can either give you the radius and say find the period, or I can give you the period and say what's the radius of the space station we need to build. Okay, fair enough? Or I guess I could give you both of those and ask you to figure out what percentage of gravity we're getting, and I think I do one in the homework, but that's a bit tricky. I don't think I asked one on the test. So, sorry, how to get rid of a squared? Okay, we'll plug and chug, but we got this. Complicated plug and chug, but we're okay. The period is going to be 4 pi squared. What was the radius? 35 divided by 0.8 times 9.8. Just a decimal. 4 pi squared r over square root. You get 13.3 seconds? Double check me. Yeah? So this needs to rotate every 13.27565, but 36, every 13.3 seconds. That'll give you 80% of mg. Now, there's some problems with this. You may have seen this in a sci-fi movie. Somewhere, period is measured in seconds. You may have seen this. Some issues. What was the radius of this? Which isn't that big. My height is actually a fairly significant portion of this radius. My head would actually feel a slightly different gravity than my feet. In this situation, you would almost always feel like, until you got used to it, you were about to fall backwards. You would just always feel slightly off balance. And so there'd be a fair bit of throwing up for the first few days until you got used to it. And we're not quite sure what the long-term effects would be if you lived on this for several years. If your brain is at a slightly different acceleration as your feet, or if your heart is at a slightly different acceleration as your feet, we're not quite sure what the long-term physiological effects would be. So if you're going to do this, you would want to make it a significantly larger radius so that a person's height is a pretty small fraction of the radius, and so the acceleration on your head versus your feet is, within a couple of percentage points of each other. Then you'd probably be okay. Nick, what's B want me to find? Okay, now frequency is symbolized by the letter F, lowercase. Nick, there is an equation that relates frequency on your formula sheet. What does it say? Frequency equals F equals? Yep. What did we find in part A? Take your calculator. 1 divided by answer button. This is rotating with a frequency of 0.0753 hertz. If you know frequency, you know period. If you know period, you know frequency. On your quiz, I gave you one question where I gave you the frequency. I gave you the period. It's the reciprocal. 1 divided by that. Okay. Suppose the astronaut begins to climb a ladder that leads to the center of the space station. At what radius will the astronaut feel 30% of his weight? Will that work, Mr. Dewick? As r gets smaller, so here's our equation for fake gravity. As this number gets smaller, would this number get smaller as well? I think so. Okay? We just get rid of that. In other words, if I put a smaller r there, I'll get a smaller answer, so a smaller percentage of gravity. Okay, yeah. As you climb towards the center, gravity would get weaker and weaker. So, Connor, what C want me to find? Nope. Too easy, I know. What's it want me to find? Radius. At what radius? We're still going to start out by saying normal force is what's pushing me in a circle. So this is who's winning, normal force. Who's losing, no mg out in outer space. We're away from any planets, so no loser. What do we want the normal force to be, Connor? Yeah, 0.3 mg. And that's going to equal AC. Which version of A are we going to use? The one with the V in it or the one with the T in it? Sorry, what? Why the one with the T in it? Is that what I found in part A? Yeah? Would the period of rotation be the same closer to the center? If you're on a merry-go-round, here's our top view of the merry-go-round. Josh, if you're standing here, and if Nick is standing there, we're rotating this way, will you both rotate in the same amount of time? Or will one of you somehow get ahead of the other person? Same time. Will you both rotate with the same speed? No, that'll be different. That depends on your location. But the period going to be the same for both of them because they're not going to one's suddenly not going to get ahead of the other person and start going around in less time. Is that all right? Okay. So I'm going to use the 4 pi squared r over period squared. Oh, can little kids and grown-ups live on a space station together if we rotate it for fake gravity? What's Andy? Connor, what did you say this wanted me to find? I don't think so. You're way overcomplicating this. At what? What's it want me to find? Radius. Okay? That's it. So what are we going to get by itself? Which is what letter in here? Yeah. I went to go see a pirate movie the other day, but I couldn't get in because it was rated R. Okay. He looked like he needed something. So, how am I going to get the r by itself? Well, what's the 4 and the pi squared doing to the r? So, what about the t squared? Yeah. This is really, it's this unit that I did all that formula manipulation stuff for you last year because I don't have to try and reteach you everything. I can set it up and then walk away. Set it and forget it, as the old commercial used to say. So you're telling me, Noah, and I think you're right, that 0.3 g times t squared divided by 4 pi squared, that equals r. But do you mind, Noah, can I put the r equals on this side? Because that's where we're used to seeing it by itself. Okay. So it's going to be 0.3 times 9.8. What was the period? 13.3? All over 4 pi squared. Thank you. I would have forgotten that. Squared candy for you. I have the frequency still on my calculator, so I'm going to reciprocal it again to get the period back. 1 divided by. In fact, I have a reciprocal button. You may have noticed you have a little x to negative 1 button or a 1 over x button. That's because that reciprocal thing happens fairly often in physics, and so there's often a dedicated button. You don't have to use your answer button, but you know I tend to. So I've got the 13.27565199 back. So it's going to be 0.3 times 9.8 times answer button squared divided by bracket 4 pi squared. Again, make sure you use your pi button. Don't use 3.14. What was the overall radius of the space station? So I know my answer's got to be less than 35 because I'm climbing up. Ooh, wow. It's always nice when something works out almost evenly with all these pies and things. You get 13.125, so 13.1. Little more than halfway back to the center. Oh, 0.5, Mr. Duick? Wow, I'm slumping. Hey, Wes, what would the fake force of gravity be at the center of the space station? What's happening as you're climbing the ladder to the fake force of gravity? Getting bigger or smaller? We just, I think, showed it's 30%, 13.1 meters in. So what's the force of gravity dead center? 0. Okay? There will be a little weightless. So if we do ever build large community-sized space stations and rotate them, there would be a 0 gravity zone right along the axis, right dead center. And there'll be some neat stuff there. Now, you might have some scientific research going on there, but almost certainly you'd have at least part of it be some kind of a recreation area. And just slightly off from the center, there might be an area where gravity was only, let's say, 1%. That might be so weak that you could strap some fake wings on your arms and actually fly like a bird and have some fun doing that. If we do ever build, massively large community-sized space stations and use rotation for fake gravity, there'd be some neat stuff along that central axis. Okay. So that's one neat horizontal circle, artificial gravity. Last day we looked at cars going around corners, horizontal circle. The Gravitron. I like example 2, I like example 2, I like example 2. Example 2 is a nice question. Oh, I'll even be more blatant. There's going to be a Gravitron on your test. What's the Gravitron? That's the ride where you lean back against the wall and then it starts to spin. And then there's 2 versions. There's one version where the ride stays horizontal and the floor drops out from underneath your feet. Or there's another version where the ride tilts 90 degrees. So when you're at the top, you're like a bucket of water. When you're spinning it around your head, you're at the bucket at the top and a bucket at the bottom. Okay? So this is the type that stays horizontal and the floor drops away. The Gravitron spins its riders in a circle. If the ride has a radius of 4.8 meters, which is about what Playlands is, and it rotates every 2.5 seconds, A. Huh. Ariana, what's A want me to find? Hey, what's mu? I don't know. What's mu with you? Okay. Karin, what might this be a good job for? If they're asking for a mu, almost certainly. And I gave you a lovely picture, so let's label the picture here. Let's put a dot right by the person. What are the forces acting on this person? Get the obvious one. We're back on Earth, so and which way would gravity be? Down. Are they sliding down the wall? Are they sliding up the wall? So I know there's an arrow pointing this way. I gotta be honest, I'm not yet quite sure what it is, so hold off. But I know it's there. What else? Oh, what path are we tracing out? Where must there be an unbalanced net force pointing? What force is that? What? Ah, that's the wall, the surface. Like the artificial fake gravity, that's the normal force. So here's my question. What's that up arrow? Would the Gravitron work if you were laying against ice? No. Turns out no. Okay? You need friction to hold you there. Yeah, okay. Friction. There's 2 equations. There's a vertical equation and a horizontal equation. The vertical equation, who's winning? It's a trick question. Ariana, are we accelerating down the wall? No. Are we sliding or accelerating up the wall? No. So I'm going to argue that friction is the same size as gravity. You okay with that? I'm going to argue that mu times the normal force equals the same size as gravity. I don't know the normal force. And I'm not going to say, oh, but look, because it's a bit trickier, because what path are we tracing out? Okay, here's my vertical force equation. Now I'm going to write down here a horizontal force equation. What path are we tracing out? So I think I can say normal force is what's pushing me in a circle. Normal force equals m AC. Which version of A am I going to use? The one with the V in it or the one with the T in it? And how do I know? How do you know? They gave me or mentioned period. Okay. 4 pi squared r over t squared. What's the normal force equal to? Wherever I see the normal force, what can I replace it with? M 4 pi squared r. Oh. So you're telling me that I can write this equation as mu m 4 pi squared r over t squared. That equals mg. Huh, that was handy. Oh! Can little kids and grown-ups go on this ride? Why? Well, that's handy. What were we trying to find? How do I move the 4 pi squared r over? How do I move the t squared over? I mean, complicated plug and chug, but still, I would argue technically plug and chug. So you're telling me it's going to be 4 pi squared gur. I stuck the G in front of the R just because I saw the gur and I went, I bet you I'm doing this right. It can't be a fluke because there's that good old gur again. Oh, no, that's wrong, Mr. Dewick. I got to divide it. It's going to be big G t squared. Don't get carried away with that gur, Mr. Dewick. Is it big G t squared over 4 pi squared r? Okay. Oh, I said big G. Yeah, little g. So it's going to be 9.8. I scrolled down. What was the period? Was it 2.5? Squared all over 4 pi squared. What was the radius? Again, I strongly encourage all of you to try these so that you know where your pi button and your pi squared and all that weird stuff is. I'm hoping I get a mu between 0 and 1 because I was making up numbers, but I was trying. I've been on this only once at Playland. Normally when we do our amusement park physics, this ride is owned by the P&E, not by Playland. And so they normally don't bring it out. But a couple of years ago, since one of the roller coasters was down, they brought out the Gravitron, and I finally got to go on it. I used to introduce this question by saying one of my great shames is I've never been on the Gravitron, but finally I've gone on it. Now what I would love to do is go on it with a bunch of tennis balls and play catch with the person across from me, because we would see that strange Coriolis effect where to us it would appear that the ball was suddenly zigzagging going sideways. So that would be really neat to try. Did you get 0.323?
Yeah.
So not too big. Usually when you go on this ride, you're either laying against some rough plastic fabric or just some sticky, rubbery, plasticky, cushiony stuff. So they've got a coefficient of friction there and you're okay. Oh, and that would be bare minimum. If that's all they had at this period of rotation, you would feel like you were about to slide down. So I'm sure they'd go a little bit faster or build a big safety margin in or whatever. Oh, cool. What's B want me to find, Allie? Okay. V. Is there an equation for centripetal speed?
Yeah.
What? That's for acceleration, thank you very much. Is there an equation for centripetal speed? I'll go there if I have to and get the V by itself, but isn't centripetal speed distance, 2 pi r, over time? So let's double check. Do I know R? Do I know the period? I would use this one because I'm using data they gave me. But this would be how fast you're traveling. And remember, that speed is what we called tangent to the radius at 90 degrees to the center. So it's going to be 2 pi 4.8 divided by, and this t does not have a squared. 12.1? Okay. What's the frequency of this ride? Frequency is 1 over the period in the same way that period is 1 over the frequency. So I could have given you this question, but instead of telling you that the period was 2.5 seconds, I could have told you that this ride is spinning with a frequency of 0.4 hertz. That means this rotates what? 0.4 cycles per second, as opposed to 1 cycle every 2.5 seconds. Hertz is how many cycles per second. I have here, show Gravitron picture. I think I got a good picture here. Must be in the video clip section. Here you go. Okay. But I would also say he's feeling, because this is a pretty small radius, he's feeling a different G on his head than he is on his feet. And so you would also feel like you were about to tip over. You would just have to balance yourself a little bit. Okay. Example 3. This picture shows a frictionless tabletop in top view. We're looking down at it. The mass is 4.15 kilograms. It's attached to a 2-meter long string, and it's moving at 2.5 meters per second. Write force equations for the string tension. This is tough to visualize. I'll show you what we're doing. Cleo, what does this want me to find? Like you're feeling right now, tension. Okay, what are the forces acting on this? Get the obvious one. Which way would gravity be? I think into our page, because it's a top view. That's tough to draw, so I'm not going to stick it on here. I am going to say, is it sinking into the ground like Quicksand? Is it flying like Superman? There's a normal force coming out of the page, and I think it's the same size as gravity. I'm going to leave them off, because I don't know how to draw them. This is why, for the car going around a corner question, I drew that front view so I could see everything, but I'm not going to do that here. Instead, I'm going to say, what path is this tracing out? So there has to be a force pointing which way? Toward the, what force is that? The string? Yeah. I think my equation is tension is what's pulling me in a circle. And here is where I have done you a terrible disservice. Here's where I've taught you wrong. Because that T, capital T on the left is tension, but capital T inside your equation would be period. Have I mentioned that we just don't have enough English letters to go? We don't have enough English letters to go around. And so all I'm going to say is you'll just have to mentally keep them straight. Now, here, did they give me period or speed? So I'm not going to be using the circular motion equation with the T in it, but it might happen. And all I can say is don't think, oh, those T's cancel, or those is T squared or something. This is where I really, for tension, I should use F with a subscripted T, and I don't. Always comes back to bite me in this question right here. Anyways, tension is equal to, I guess it's going to be then, Noah, the V squared over R. Don't forget the M, because earlier you had said acceleration. No, force is mass times acceleration. But otherwise, this is plug and chug. How big is tension? 4.15, 2.5 squared, all over 2. I forgot to put, did I put the M in? I did. Sorry, can you use what? If you want, yeah, if you want to, yeah. If you wanted to put that, yeah. And I keep meaning to change my Physics 11 teaching, and I keep forgetting, and by the time I remember, I'm partway through the forces unit, and I'm like, geez, do it. So, do y'all get 13.0 newtons? What if we wanted to spin twice as fast? How many times bigger would the tension be? 4 times larger. Okay? 4 times larger. Gonna skip example 4. And normally I look at the banked corner. This year I'm gonna skip the banked corner even though it's totally cool. So we're going to skip example 6. Put your pencils down. The final lesson of the year, of the course. Well, I shortened it, but who was asking about rollercoaster loops? Was it Noah? Or, no, Wes, this is for you, but all of you. How many of you have been on a roller coaster with a loop before? None of you have. Sorry, I phrased that wrong. How many of you have been on a roller coaster with a circular loop before? None of you have. We're going to look at this example here and show why roller coaster loops are never circular. Okay? Circular would not be good. Example 1. A roller coaster. Now, normally I would say I like example 1, I like example. I'm not going to put example 1 on your test this year because I'm cutting corners, but it's really cool. A roller coaster barely makes it around a vertical loop of radius 4 meters. Find the minimum height that the coaster needs to start from at the top of the hill. In other words, you're designing this ride, Karn, and you want the coaster to make it through the loop. What's the minimum height you got to start it from? And then B, find the normal force when the coaster returns to the bottom of the loop. And C, how many G's is this? Okay. What does this question want me to find? Part A. Is there a change in height? Is there a change in speed? Is there a yucky, curvy path? How might we start this out? I think we'll try starting out with conservation of energy. Except I'm going to let initial be right here. I'm going to let final be top of the loop. I got it. That's where I focusing to make sure we make it through. Okay? So we're going to start out like this. KE initial plus PE initial equals KE final plus PE final. And we're going to, Wes, ignore heat. We're going to lube this roller coaster down pretty good. Are any of these zero? Kinetic energy is zero if we're at rest. Let's assume we're starting out at rest, because this is minimum. So what's the minimum height we need? If we had some speed, we don't need to build that hill as high, but let's assume that we're starting out at rest. Are we at rest at the top of the loop? No, if we stopped there, the roller coaster is going to come crashing down. So we're not going to do that. Potential energy is zero when we're on the ground. Are we on the ground at the initial location? Are we on the ground at the final location? Yeah, okay. Well, mgh initial equals a half mv final squared plus mgh final. Wes, can little kids and grown-ups go on your roller coaster at least? Yeah. Why? Well, that's handy. Okay. So we end up with this. GH initial equals 0.5 V final squared plus GH final. And I'll divide by G eventually, but let's walk through and see if we know this. V final here, I don't know. But wait a minute. At the top of this loop, what path are we tracing out? You know what right here is a good job for? What are the forces acting on this coaster, Wes? Get the obvious one. Good. What else? Okay. Yeah. Now, if, as the question says, we just barely make it through that loop, what that means is the normal force equals zero. Now, let's do this. Who's winning? They both are. So my initial equation would look like this. Gravity plus normal force is what's pushing me in a circle. But now for the normal force, you can put a little equals zero and cross it out. And that's because we're barely making it over, which means we're going to feel weightless. We're going to feel like we're about to fall out. Okay? So I get this. Mg equals M. Wes, which version of AC do you think I want to use? The one with the period in it or the one with the V in it? Why? Because that's what I don't know. So not that they gave it to me, but I want this. Oh! Are we okay for... Yeah, are we... M's cancel? Yeah. Now, I heard Carter say square root of GR. I'm actually not going to do that. I'm going to be clever. I know, Carter, you're not used to being... But I'm going to be clever. Okay? Here's why. Carter, can you read to me these three things? 0.5 what? V final what? V final what? I'm going to get the V squared by itself. What, I mean, I could get the V by itself, but when I put it back in here, I'm going to square it right away. So why don't I just get the V squared by itself? So I'm going to say not V equals the square root of GR, but I am going to say it turns out V squared equals GR. And that can go into my conservation of energy G equation. I get this. GH initial equals 0.5 GR plus GH final. Oh. What? Would this roller coaster work on the moon without having to change anything? Yes. Would this work on Mars? Yes, because it turns out this is independent of your planet's gravity. As long as you have any gravity, this will work. Doesn't matter which planet you're on. This, I want to talk about the final height. So we're going to do a little thought experiment. What do I call the distance from the center to the edge of a circle? Radius. What letter? So you ready? Follow along with me. How far from here to here? R. Yes? How far from here to here? How far from here to here? How far from here to here? How far is the total distance? It's not R squared. 2R. I'm also going to make a little note. Hey, H final is 2R. So I'm going to get this. Your minimum initial height is 0.5R plus 2R, which I can do in my head. You know what 2R plus 0.5R is? 2.5R. If you're a roller coaster ride designer, in the same way all of you have memorized the 9.8 and the F equals what MA, I'm willing to bet any ride designer has memorized that for a circular loop, you better start out at least that high. And in fact, Wes, we can calculate it. What was the radius? 2.5 times 4. I think that's 10. Double check me. I always have loved this answer because it's so clean. Look at what we started with. Look at what we had over here. And we end up with, oh, as it turns out, gravity is irrelevant. And if you want to build a roller coaster, make sure your first hill is 2.5 times the radius of your roller coaster if you're using a circular loop. Now, you heard me say, how many of you have been on a circular roller coaster with a roller coaster with a circular loop? And when you raised your hand, I said, none of you have. Here's why. What does B want me to find? Where? Okay. At the bottom. Well, you know what this is a good job for? Okay. What are the forces at the bottom? Get the obvious one. What else? Normal force. Right as they're entering this loop, what path are they tracing out? So where must the winning force be pointing? Toward the? So who's winning? Who's losing? Equals. Well, since they're talking about, what were they asking in part B? Normal force. We're going to use speed. I'll show you why in a second. So here was part A. Part B, we're going to have normal force minus mg equals mv squared over r. So the normal force is going to be mv squared over r plus mg. Do I know m, 50? Do I know G, 9.8? Do I know R? Do I know V? You know what this is a good job for? Conservation of energy, G. Because the speed is going to be all of this potential turned into kinetic down here. So I'm going to draw the line. Now, for part B, final is going to be right there. Initial still top of the hill. And we have this. I'm going to cut corners a little bit, but I think all of your initial potential becomes all of your kinetic final. Because we started at rest, Karn, and at the bottom, right at the beginning of the roller coaster, how high are we? On the ground. And I'm going to do the same trick as we did before. I'm going to get an expression for V squared. So it's going to be this. mgh initial equals a half m V final squared. Little kids and grown-ups. And I'm going to get V final squared equals 2G H initial. Wait. What was H initial? What did I circle earlier? 2.5 times the radius. Let's put that in. 2G times 2.5 R. Wes, in your head, what's 2.5 times 2? So VF squared is 5 GR. We get this. The normal force right at the bottom is M. There's an R. What can I replace the V squared with? Plus mg. M5 GR over R plus mg. That first fraction, is there an R on the top? Is there an R on the bottom? So, and Wes, here's what I end up with. The normal force is going to be 5 mg's plus 1 mg. What is 5 mg's plus 1 mg? So it's going to be 6 times 50 times 9.8, which is what? By the way, how many G's are they pulling at the bottom? If your normal is 1 mg, how many G's are they pulling at the bottom? How many G's are they pulling at the bottom? 6. You're pulling 6 G's at the bottom, which is most people can't handle. None of you have ever been in a circular roller coaster loop. What'd you get? 2,940? 2940? Newtons of force. Divide that by 9.8. How many kilograms would they feel like they weighed at the bottom? Okay? And the answer to part C, how many G's are you pulling? 6 G's. The earliest loops were actually circular. They weren't roller coasters. They were like a metal water slide. So this went straight down. There was one, I think it was in Coney Island, and people would pay, this was in the 1880s, people would pay big bucks, but they had to have ambulances and nurses stationed at the bottom because people would regularly come off with whiplash or nosebleeds. But that was great. We loved it. We don't build circular roller coaster loops anymore. The closer the roller coaster loop is to a circle, the higher the G-forces are. Most roller coaster loops are built in what's called a clothoid loop. A clothoid loop is teardrop shaped, like that. So if you ever look at a roller coaster loop from the side, the more elongated it is, the easier it is to go through that one. You will still be, I'm upside down, but you won't feel the G-forces as much. If you go to Playland, if you go to California Adventure at Disneyland, the California Screaming Coaster, that loop to the naked eye looks almost bang circular. It's not, but there, if you ever go on there, you're pulling a fair bit of G's. I've been on there enough times that now when I see I'm coming to the loop, I will either lean forward and then try and straighten my head out during the loop. I can't. Or I'll just do this with my arms in the loop, and lifting them up is really, really, really tough. Okay. So a dead circular loop, perfectly circular loop, 6 G's, not good. Put your pencils down, look up. What's your homework? Can you get out the ultimate circular motion review? This big one here. Is there any homework attached to it? Again, probably not. These are questions that I think are fair game. Okay? Now, you can ignore this equation and this equation because I did not get to the gravitation stuff. Everybody found it okay? I'll wait a little bit longer. 1 is good. 2 is good. 3 you can put a star next to. I'll assign it. It's not on your test, but we just did it. You want the minimum height, it's going to be 2.5 times the radius because we just calculated that. Skip 4. Skip 5. Skip 6. Skip 7. 8 is good. Skip 9. 10 is very tricky. That's harder than I'll ask you on the test. You can look at my answer key showing all my steps. So this is a Tarzan swing, and you can assume then that Tarzan is holding the rope dead horizontal, and this is the circle that he's tracing out. So this is I would start out with some conservation of energy, G, as well. See if you can figure it out. And it's going to ask you what the tension is at the bottom, and you'll realize it's also really big. Newsflash, it'll be 6 Gs, because this is the same physics as a roller coaster loop. That's why on rope swings, people, when they're going to lose their grip, where are they going to lose their grip? When they're at the very, very bottom, because where's the tension coming from? The rope, but forces come in pairs. So if you're applying a force to the rope, the rope is applying a force to your hands, and you might slip out. So 10's tougher than I'll ask, but it's rope swings. Those are cool. Skip 11. Skip 12. Skip 13. 14 is good. 15 is good. 16 is good. Hey, everything on that page. Skip 17. Skip 18. Skip 19. Actually, you can do it, but it's physics 11. But I'll skip that. 20 is good. 21 is good. 22 is good. Skip 23. Skip 24. Skip 25. Skip 26. I like number 27. I like number 27. 27 is a nice question. 28 is good. Skip 29. Skip 30. Skip 31. "32 is okay. Don't let it panic you. You can look at my answer if you want, but basically it's saying, okay, when this is at rest, tension is 14 newtons. If we swing it, what's going to happen to tension? Bigger, smaller, or stays the same? And prove it. I think a good free body diagram will do it for you. You can make up numbers if you want to, but that's not too bad a one. 33 is good. 34 is good. 35 is good. Skip 36. Skip 37. Skip 38. Skip 39. Skip 40. 41 is good. Skip 42. Skip 43. And we're running out of questions, I think. Oh, 44 is good. 45 is good. Skip 40. No, 46 we can do. Yeah, you got the numbers on your formula sheet. Look at number 46. It says, what's the magnitude of the Earth's centripetal acceleration as it orbits the sun? Which answer would you cross out just by glancing at it? Yeah, I don't think it's 9.8. I don't think the sun's gravity attraction on the Earth is not. That's the whole, I got to give you another wrong answer to pick for. 9.8. So hopefully you're clever enough to spot that. Skip 47. Skip 48. Skip 49. Skip 50. Skip 51. Yeah, scholarship questions. Skip 52. 53 you can skip. 54 you can skip. Oh, that's a cool one. 55 you can skip. So I think we're skipping all the scholarship questions. Okay. So most of you still haven't handed in lesson 1 or lesson 2 or lesson 3. Start there. Work your way through there. I see you on Thursday. Thursday, we're going to mark the take-home quiz. Start with the take-home quiz. We're marking the take-home quiz Thursday. Thursday, I'd love to give you another take-home quiz and mark it in class, and then we'll decide whether we want the test Friday or Monday, but we'll decide that Thursday. Don't make your decision yet, okay? Also, if you're planning on doing a rewrite, sign up for a rewrite. The only one you can't do a rewrite for is the circular motion test, because there's no way I can, well, if we wrote it Friday, I guess I could get it for you. I see you Monday. I could get it marked for the weekend, and then you could include the. Basically, that would be the advantage of writing on Friday, is I could add it to your rewrite list if you wanted to. All right, my angels, the remainder of the class is yours. Use it.